Hello and welcome back to Physics for Cause. In this particular video, I will be going to explain you about Schrodinger wave equation, which is the fundamental equation of wave mechanics. Basically, the Schrodinger wave equation is the differential equation of de Broglie waves. In the previous videos, we have discussed about that de Broglie wavelength is denoted as lambda is equal to h upon p, where h is the Planck's constant and p is the linear momentum, and lambda is the de Broglie wavelength for matter waves. So to deduce Schrodinger wave equation, we need to understand two most important parameters in quantum mechanics. Number one is about the energy operator and second is about momentum operator. So let us consider the case where we would consider the fluctuating parameter. The wave function is denoted by the symbol psi. Psi can be considered as a fluctuating parameter for matter waves. Now, if a wave is moving with a velocity v and time taken is time t, so for matter waves, the wave equation can be represented as psi is equal to a e to the power minus I omega t minus x upon v, where psi is the fluctuating parameter, a is the amplitude of the matter wave, here omega is the angular frequency, t is the time taken, x is the displacement, and v is the velocity of the wave. Now it can be transformed to the most simplest and the most basic form by applying the principle that omega is equal to 2 pi nu, where nu is the frequency. This denotes the frequency and nu is the angular frequency. Nu is the angular frequency. Okay, so we can transform this equation into another one. Psi is equal to a e to the power minus 2 pi nu I t minus x upon v. We can also write the velocity can be written as nu lambda. Velocity is equal to frequency into wavelength. So it can be written as psi is equal to a e to the power minus 2 pi nu I t minus x upon nu lambda. So what can we do? We can just multiply the psi to the inside of this particular bracket. We can shift. So psi can be written as a e to the power minus 2 pi I nu t minus x nu over nu lambda. This nu and nu will cancel out. So psi can be written as a e to the power minus 2 pi I nu t minus x upon lambda. So on multiplying and dividing the numerator and denominator by h is a Planck's constant. Planck's constant. So we can transform the above equation psi is equal to a e to the power minus 2 pi I over h. Here we are dividing and again h nu t minus hx over lambda. Here we are multiplying. So the effect is negligible. So we know that energy is written as h nu or hc upon lambda. So in place of h nu, we would write energy, and we also know that P is equal to h upon lambda from de Broglie equation, which we have seen in the previous videos. So in place of h upon lambda, we can substitute P. So psi is equal to a e to the power minus 2 pi I over h e t minus px. This is the equation for the fluctuating parameter. We also know that the reduced Planck's constant is denoted by h cut is equal to h upon 2 pi. So we can transform again this equation into psi is equal to a e to the power minus I upon h cut et minus px. This is the equation for the free particle which is fluctuating. This is the equation for a free particle. And this is the one of the most important equation when we are going to talk about Schrodinger wave equation, because this equation is helpful to determine the value for energy operator as well as for the momentum operator. So now we can determine the value of energy operator by using this particular relation. So energy is the function of time. Energy is the function of time. So we need to differentiate. Let us consider this as equation number 2. We need to differentiate equation number 2 with respect to time t. Okay, so we can consider as del phi psi over del t is equal to a e to the power minus I over h cut et minus px and minus I e over h cut. How? By using this particular relation, d over dx e to the power minus ax can be written as a e to the power minus ax minus a. It can be written as. So this particular relation is the psi itself. So we can write as del psi over del t is equal to psi minus IE over h cut. So we can rearrange itself. Del psi over del t is equal to minus IE psi over h cut. So from here we can get the expression for the energy operator. How? So E psi is equal to minus h upon I, h cut upon I del psi over del t. And if we are going to talk about alone the energy operator, we get minus h cut upon I del over del t, as the psi and psi is neglected here. So this is about the energy operator. Now we can convert it into the form of some else. Now we can what else we can do? We can just make energy operator positive by multiplying it by iota and dividing it by iota itself. So we get E is equal to negative h cut I del over I square del t. So it can be written, I square can be written as negative 1. So E is equal to negative h cut I del over negative del t. So negative and negative got cancel out. So E is equal to I h cut del over del t. This is the equation number 3 which we need to remember in case of energy operator. Now to understand the concept of momentum operator, we know that the momentum is the function of x. It is the function of the displacement. So we need to differentiate psi with respect to x. Let me show you this particular expression. This particular expression need to be differentiated with respect to x so that we get the momentum operator. So we need to find del psi over del x. So now let us perform this particular calculation. Okay, so del psi over del x is equal to a e to the power minus I by h cut et minus px. Here I upon h cut into p. So what we will get, del psi over del x is equal to, this particular term is the psi itself. So we can write psi I upon h cut into p. So on arranging, we get del psi over del x is equal to I upon h cut p psi. So we need to determine the value of p psi. So we can write p psi is equal to h cut upon I del psi over del x by just rearranging itself on rearranging. Now the psi and psi got neglected here, so p is equal to h cut over I del over del x. This is the momentum operator. But as we have discussed in the energy operator, we had converted iota. We have made this particular relation in such a way that iota does not come into the denominator part, so that our calculation becomes simple. So same principle we will apply here in the case of momentum operator. So what else we will do? We will multiply and divide this particular relation by iota itself. So we get p is equal to I h cut del over I square del x. We know that iota square is -1. So here we get p is equal to I h cut del over -1 into del x. So we can write it as minus I h cut del over del x. This is the momentum operator and it can be considered as equation number 4 here. So we need to remember these relations, energy operator as well as the momentum operator. Now we can now evaluate, or we can now deduce the Schrodinger wave equation. Schrodinger wave equation. Now let us move toward the most important topic, is Schrodinger wave equation. As I have discussed it before, that it is the fundamental equation of wave mechanics. It is the fundamental equation of wave mechanics. And basically it is the differential equation of de Broglie wave. De Broglie wave, which is lambda is equal to h upon p. Okay. So now if a particle is moving with a velocity v, so the total energy is represented by the sum of kinetic energy and potential energy. Okay. And in the case of de Broglie wavelength, we have already derived the expression that kinetic energy is written as p square upon twice m. In case you don't, you can switch towards the previous video of de Broglie wavelength. And the potential energy can be written as capital V. So this is the particular relation or the equation which is denoting the total energy of the particle. This is the total energy of the particle which is moving with a very high velocity. Okay. Now we need to multiply this equation with psi. So we will write multiply the above equation with psi. So we get E psi is equal to p square psi upon twice m plus v psi. So this is the particular result which we have got, and let us consider this as equation number. What we have considered the equation number before, we have considered 4, so this can be considered as equation number 5th. Now as we have discussed about energy operator from equation number 3rd, so we can write from equation number 3rd we have got the value of E energy operator as I h cut del over del t, and from equation number 4th we get p is equal to minus I h cut del over del x. So now substitute these values, substitute the value of energy here and the value of momentum here. So now let us perform our task. So put E and P in equation number 5th. So what we will get? Let us consider E psi is equal to p square upon twice m psi plus ka v psi. So E can be written as I h cut del over del t and psi here as it is p square. It means to say that I h cut del over del x whole square into psi upon twice m plus ka v psi. Now on rearranging itself, we will get is equal to minus h cut square upon twice m del square psi over del x square plus का v psi. So this is the equation which is known as Schrodinger wave equation. And here we can see it very clear that it depends upon the time t. So this particular equation can be considered as time dependent Schrodinger wave equation. Okay, so time dependent Schrodinger wave equation is the equation where the wave function explicitly depend upon the time t. So this is the time dependent Schrodinger wave equation. But in most of the cases, the energy or the wave function does not explicitly depend upon time t. The case where the function does not explicitly depends upon time t. So we need to remove the factor of time taken. That is why time independent Schrodinger wave equation come into existence. And this is one of the most interesting and the most fruitful equation in the field of quantum mechanics, as this relation is very helpful to understand about particle in a one-dimensional infinite depth box in a step potential, to understand the concept of tunneling effect or potential barrier and the harmonic oscillators as well. So now we need to understand the time independent Schrodinger wave equation. So as far we have discussed about the Schrodinger wave equation can be written as by this particular relation which we have derived here. Now, what was the base? The fluctuating parameter which was written psi is equal to a e to the power minus I over h cut e t minus px is the base of this particular Schrodinger wave equation. So what we will do, we will write it as a e to the power minus I upon h cut e t and e to the power I over h cut into px. Here minus and minus got plus sign. What we have done is we have considered this as a part and this as a part. Okay, so we need to transform it in a way that the factor of time is neglected. So what we can do, from here this particular relation we can write a and e to the power I by h cut px as a separate quantity. So psi is equal to a e to the power I upon h cut px and the remaining word e to the power minus I by h cut into et. Now, the most important part. We can consider this as a separate quantity can be written as psi naught. So we can write it psi is equal to psi naught e to the power minus I by h cut et. Now, differentiate psi with respect to time t. So del psi over del t is equal to psi naught as it is, e to the power minus I upon h cut et, again minus I upon h cut into e. Okay, so this is the relation when we will differentiate psi with respect to time t. Why we have done this? Why? The question arises why. We have done this particular result so that we can put the value of del psi upon del t in this particular relation, and we need to also determine the value of del square phi over del x square to put in this particular relation. So let us consider this as a equation, suppose A. Okay, So what we have done, we have determined the value of del psi upon del t. Now we have to determine the value of del square psi over del x square. So let us perform our task. So now differentiate psi with respect to x. So we get del psi over del x is equal to minus del psi naught upon del x e to the power minus I upon h cut et. But in this particular relation of time dependent Schrodinger wave equation, we have second order derivative of psi with respect to x. So we need to differentiate it again. So del square psi over del x square is equal to del square psi naught upon del x square e to the power minus I upon h cut et. Now substitute the value of del psi upon del t and del square psi over del x square in equation number A. So this relation and this relation need to be substituted in time dependent Schrodinger wave equation, here this particular expression and this particular expression. So now let us perform our task. So we can consider I h cut del psi upon del t is equal to minus h cut square upon twice m del square psi over del x square plus ka v psi. This particular expression is the time dependent Schrodinger wave equation. Now in place of del psi upon del t and del square psi upon del x square, substitute the new result. So I h cut psi naught e to the power minus I e upon h cut into t minus I e upon h cut is equal to negative h cut square upon twice m del square psi naught upon del x square e to the power minus I e t upon h cut plus v psi naught e to the power minus I e t upon h cut. Okay, so this is the particular expression which we have got by substituting the value itself. Now we can arrange this particular expression as follows: I h cut psi naught e to the power minus I e t upon h cut minus I e upon h cut. Here minus h cut square upon twice m del square psi naught upon del x square e to the power minus I upon h cut et plus का v psi naught e to the power minus I e t upon h cut. So we can cancel I upon h cut et. This factor and this factor got cancelled out. So we get the another expression, and one another thing which we can cancel out is about h cut here, and here we can get something, the new expression as follows. So E psi naught is equal to minus h cut square upon twice m del square psi naught upon del x square plus ka v psi naught. So this is the particular expression which we have got. Now on rearranging itself, we get minus h cut square upon twice m del square psi naught upon del x square plus e minus v psi naught is equal to 0. This is the time independent Schrodinger wave equation, where the function does not explicitly depend upon the time t. So we can also rearrange itself as follows: del square psi upon del x square plus ka twice m upon h cut square e minus ka v psi is equal to 0. So this is the time independent Schrodinger wave equation. When we are going to talk about in a particular direction, that is about the x-axis. So what we have learned today is about, first of all, the wave equation, which is noted as psi is equal to a e to the power minus I upon h cut e t minus px. From here we have derived or deduced, derived is not the correct word, we have deduced time dependent Schrödinger wave equation, time dependent Schrödinger wave equation, which is denoted as I h cut del psi over del t minus h cut square upon twice m del square psi over del x square plus ka v psi. And from here we also have discussed about the time independent Schrödinger wave equation, where the function does not explicitly depend upon the time t. So we have discussed del square psi upon del x square plus twice m upon h cut square e minus ka v psi is equal to 0. And this is the particular expression. This particular expression is fruitful. It is very much fruitful result to understand the concept of four things. Basically, it serves as an application or a base for the four important factors. So application of Schrödinger wave equation. Schrödinger wave equation. So first of all, we can understand the concept of particle in a box, and box is one dimensional and infinite depth. Second, we can consider about the case for the step potential. Fourth can be considered about the square potential. Next, we can consider about the potential barrier or tunneling effect. And fifth, we can consider about the case of harmonic oscillator. So I hope that you must have enjoyed this particular video where I have discussed about the Schrödinger wave equation. These 5 topics we will discuss in the upcoming videos one by one. So thanks a lot for watching this particular video.